This meeting is being recorded.
It's my pleasure to welcome Lucia Martin-Mirchan of the University of Waterloo, who will speak on topological properties of compact closed G2 manifolds through compact quotients of Lie groups.
Okay, thanks a lot for the invitation to the seminar. In this talk, I'm gonna explain how compact quotients of Lie groups can be useful in order to tackle two problems on closed G2 manifolds and in the research of their topological properties. So I'm gonna structure my talk as follows. In the beginning, I will just explain basic things on G2 structures and on closed and torsion-free G2 structures, and I'll fix the notation for dealing with compact quotients of Lie groups. And then I will continue by presenting the results in the two problems that I will motivate during the first part. So let me begin by defining a G2 structure. Well, the group G2 is simply connected four-dimensional Lie group, and it can be viewed as an embedding in SO7, being the stabilizer of a certain three form that I will call a standard G2 form of R7. Here I wrote this free form with the standard coordinates of R7, but the kind of interesting is that it encodes a cross product on R7. And this three form is just the contraction of the cross product of R7 with the scalar product. So whenever we have a seven-dimensional oriented Riemannian manifold, G2 structure is going to be determined by a free form that in an orthonormal oriented frame is going to be written as the standard G2 form on R7. And in the same way, this free form will induce a cross product on the manifold. Also, one can view G2 structure from the perspective of stable free forms. We say that a free form alpha on R7 is stable if the orbit of alpha under the action of linear isomorphisms of R7 is an open subset of the free forms. Well, but it turns out that the stabilizer of such a stable free form is conjugate to G2, and one can also find a metric and a volume form using the stable form. And these are related by that equation, 6 times the metric evaluated on UV times the volume form is equal to the wedge product of the contraction of alpha by U with the contraction of alpha by B and alpha. So any stable free form on a seven-dimensional manifold is going to determine a G2 structure on the Riemannian manifold with metric, the one that we have in the that satisfies the previous equality and the orientation of that volume form. Now I'm gonna explain like general results on these manifolds. With the first result related, this is the result over here that implies that G2 can be an holonomy group for seven-dimensional manifolds. But it turns out that compact manifolds with holonomy G2 are very difficult to construct, and up to now we have like four constructions. Being the first one, the construction by Joyce, BR before resolution, and the construction of Joyce and Carigiani which is the last one to appear, is going to be somehow related with the talk. But there are like other types of G2 structure that are also interesting from the point of view of Riemannian geometry. And Fernandez and Gray classified G2 structure according to partial differential equation involving the covariant derivative of the theory form. And there are 16 types, but we are only gonna be interested in 2 during the talk. The first one is are closed G2 structures in which the free form is closed, and torsion-free G2 structures are these in which the free form is parallel, and this implies that the holonomy of the metric is contained on G2 by the holonomy principle. And there are like topological restrictions for compact manifolds having a torsion-free G2 structure. The first one is that they satisfy that the third Betti number is positive because parallel, the free form is closed and co-closed, so it determines a cohomology class. And in addition, they are almost formed, they should be formed. But let me explain a little bit about formality. I'm not gonna explain the definition, but this is a notion that comes from homotopy theory, and it studies the torsion-free part of higher homotopy groups. And the special property that formal manifold satisfies is the following. Assume that we have a simply connected formal manifold, then there is a theorem of Sullivan that says that one can compute the real homotopy groups, which are just the tensor product of the higher homotopy groups with R, that is like the torsion-free part again, but now with coefficients in the real numbers instead of the rational numbers. We can compute these groups from the cohomology algebra of the manifold with real coefficients. And I also should mention that the formality property depends not only on the cohomology as vector space, but also depends on the algebra structure of the algebra that is indexed by the weight product. And well, being formal is just kind of a weak condition, but I'm not gonna go into that. And this notion of formality is related with holonomy. And the first result in this line was the result of Deligne, Griffiths, Morgan, and Sullivan that proved that compact Kähler manifolds are formal, and there is a kind of big open question, and it is to determine if manifolds with exceptional holonomy are formal. Up to now, all the known examples are formal. And as I said before, the most that people have proved up to now is that these G2 manifolds are almost formal. So the questions I'm gonna discuss in the talk are motivated by this general question, which is which topological properties distinguish compact closed G2 manifolds from compact torsion-free G2 manifolds. If one can, and I am like motivating my questions by comparison with other geometries. And if we go into Kähler geometry, would be restated as which topological properties distinguish symplectic manifolds, because the two form is closed, from Kähler manifolds, because there the two form is parallel. So the first question is if simply connected compact manifolds admitting a closed-G2 structure are almost formal, because that's the property we know that compact torsion-free G2 structure verify. And for the moment, there aren't a proof or a counterexample. But if we compare with scalar geometries, I somehow expect that the answer to that question is negative. And because there they had a conjecture, the so-called formalizing tendency of symplectic manifolds, that wonder whether simply connected compact symplectic manifolds are formal. And the answer in that case is negative. And in this talk, I will explain that if we replace the hypothesis of being simply connected with having first Betti number equal 1, the answer to question 1 is negative. And the second question is, do compact manifolds admitting a closed-G2 structure satisfy that the third Betti number is positive? Or more generally, since the known cohomology class is determined by the free form in the torsion-free case, could a compact manifold admit an exact G2 structure, that is the free form being closed but also being exact, the differential of a true form? And again, for the moment, there aren't proofs or counterexample to that. But it's interesting because if the answer was negative, then we could discard the existence of a closed-G2 structure on the 7th sphere, because that has third Betti number equals 0. And in comparison with scalar geometries, we know that symplectic manifolds that are compact have even Betti numbers positive, because the symplectic form and its powers determine cohomology classes. But this question seems to be somehow very different to the symplectic case. And we are gonna prove, well, I'm gonna show this result, which is a joint work with Fino and Alberto Raffero, that states that if there were any, that is, that a potential compact manifold with an exact G2 structure is not the compact quotient of a 7-dimensional simply connected Lie group by a discrete subgroup in such a way that the form, the free form is left invariant. And as I promised, I'm gonna talk a little bit about left invariant G2 structure on Lie groups. We will consider a Lie group G with Lie algebra little g, and we're going to define the Chevalier-Eilenberg complex as the exterior algebra of the dual of the Lie algebra, and the differential on one form is going to be the dual of the Lie bracket, and it is extended as a derivation to higher degrees. So we have an inclusion from this Chevalier-Eilenberg complex to forms on the Lie group G, because one can extend forms on the Lie algebra to the whole Lie group using left translations, as this picture shows. And I also want to fix some notation for Lie algebras. I'm going to explain it with an example. Imagine that we have a 3-dimensional Lie algebra with a basis E1, E2, and E3 of the space of forms on the Lie algebra that verifies that the first two forms are closed, and the differential of the third is the wedge product of E1 and E2 in this case, we are going to denote this Lie algebra using Salamon's notation as 0, 0, 1, 2. And well, of course, if we have a lattice gamma that is a discrete subgroup such that the quotient is compact, then left invariant forms on the group determine forms on the quotient. And what we're going to consider are left invariant structures on this compact quotient. And these are going to be determined by a form on the Chevalier-Eilenberg complex. So that's useful because if we fix the Lie algebra, we have some differential equations like the free form being closed or being exact. But with this type of structure, what we really have is an equation for the coefficient of the free form, but it's no longer a differential equation. And in this sense, we'll say that the Lie algebra admits a closed or an exact G2 structure, because all the information of the compact quotient is encoded by the Chevalier-Eilenberg complex, which only depend on the Lie group and not on the lattice. And we, during the talk, nil manifolds and solved manifolds will also appear. A nil manifold is this type of compact quotient where the group is nilpotent. And in this case, from the nilpotency condition, one can ensure that there is a basis E1 to M of the dual of the Lie algebra in which the differential of a form can be expressed in terms of the previous generators in the list. And they have special topological properties. Nomizu's theorem says that one can compute the cohomology of the nil manifold with real coefficients by computing the cohomology of the Chevalier-Eilenberg complex. In addition, they have first Betti number greater or equal than 2 because of the nilpotency condition, because you see that the differential of E1 and E2 should be 0. And the last one is that all of them are non-formal, except for the case that they are associated to the abelian Lie group, so they are a torus. And in the same way, solved manifolds are compact quotients where the group is solvable. They have first Betti number greater or equal than 1, but this can be either formal or non-formal. So now I'm gonna focus on question 1, which was if like closed G2, simply connected closed G2 structure should be almost formal. And I said that the answer is negative for first Betti number equal 1 instead of being simply connected. So the examples of closed G2 manifolds with no torsion-free G2 structure that we have up to now can be like subdivided in 2 types. First of all, we have nil manifold and solved manifolds. I will like highlight the list Conti and Fernandez because they classified nilpotent Lie algebras admitting a closed G2 structure, and these yield examples with first Betti number greater or equal than 2 that are non-formal. And also Manero constructed a formal submanifold with first Betti number equal to 1. And later there are more examples via or before resolution that are constructed from a closed G2 nil manifold. The first example was in the paper of Fernandez, Fino, Kovalev, and Muñoz, where they construct a formal manifold with first Betti number equal 1. And in this talk, we're gonna see the construction of a non-formal manifold with V1 equals 1. So what we do is to consider a closed G2 manifold and an involution of the manifold that preserves the G2 structure. Then we consider the orbit space of the involution, and this is not a manifold because it could have some singularities. These singularities being the fixed locus of the involution. That's why we will call that as, the singularities are make this space an orbifold, and since we have a closed G2 structure on it, we will call it a closed G2 orbifold. And as I said, when we have a closed G2 orbifold, we want to obtain examples doing the resolution. So of a closed G2 such that the projection map is a diffeomorphism out of the singularities of the orbifold, and it preserves the G2 structure out of a neighborhood of the singular locus. And in analogy with algebraic singularities, we will call E the exceptional divisor, which is the counterimage of the singular locus by the projection map. So for doing the resolution, we have like two theorems. The first one is like that states that in the setup that I mentioned before, that is having a closed structure with an involution, then when we consider the orbifold, which is the quotient of the manifold under the involution, we can perform the closed G2 resolution in the case that the fixed locus of the involution, which is the singular locus of the orbifold, has an over-vanishing closed one form. And a remark is that this method, this theorem, is a simplification of the resolution method of Joyce-Carigianis, in which they did the same thing, but in the torsion-free G2 case, to obtain more examples of manifolds with holonomy G2. And on theorem 1b, one describes the cohomology algebra of the resolution in terms of the cohomology algebra of the orbifold and the singular locus. First of all, as groups, here we have an isomorphism. The cohomology group of is the direct sum of the cohomology group of the orbifold and each of the cohomology group of the connected components of the singular locus that I call Li, but these are tensor with a degree 2 class. And since the property of being formal depends also on the algebra structure, one can also have to view the product on the product rule on the cohomology algebra of the resolution in terms of the isomorphism. And here I wrote the rules in order to do so, but they are not important for the talk. And a remark is that since here the cohomology of the cohomology group of the connected components of the singular locus are tensor with a degree 2 form, then the first cohomology group of the resolution coincide with the first cohomology group of the orbifold. That is, the resolution procedure preserves the first Betti number. So I'm not really gonna explain how one can prove theorem 1A, but I will just outline what's the local model of the singularities and how can we resolve them. So first of all, to view the local model, one has to view G2 as a subgroup of, view SU2 as a subgroup of G2. So we will do this like in 2 steps. First of all, whenever we have a G2 form on R7, then it determines an SU3 structure on the orthogonal space of a vector. An SU3 structure can be viewed as a pair of forms in which omega is a symplectic 1-1 form and theta is a complex 3-0 volume form. And that's a way of viewing that property is that one can write the 3 form phi of the fixed vector E1, which the symplectic form of R6 plus the real part of the complex 3-0 volume form. And if and in terms of complex structures, one can define the complex structure as the cross product with the perpendicular vector E1. And since the space V has an SU3 structure, whenever we fix a complex plane there, we will have an SU2 structure. And conversely, if we have an SU2 structure on R4, namely the standard one, which are given by a basis of self-dual forms, here I'm seeing like omega 1, 0 as the symplectic 1-1 form of R4, and omega 2 and omega 3 as the real and imaginary part of the complex 2-0 volume form. Whenever we have this, we can split R7 as R3 times R4 and write the G2 structure in terms of the standard basis of R3 and these forms that determine the SU2 structure. Here you can see how. So now let's move to the how can we find the local model. For this, we can point that is inside the singular locus, that is the fixed point of the involution, and linearize the map by considering the differential. And this is an endomorphism from the tangent space at P to itself that preserves the G2 structure, and it verifies that it's a linear involution. Then doing some linear algebra using only these two properties, one can prove that this differential is diagonalizable with eigenvalues 1 and -1. The eigenspace associated to one has dimension 3, and the other one has dimension 4. And in addition, the eigenspace associated to -1, which is for the dimensional, has an SU2 structure that I will call like the standard one. So the local model is the quotient of the tangent at the point P by this linear involution. And then we can split the tangent space as the product of the eigenspace associated to 1 and the eigenspace associated to -1. And on the eigenspace associated to -1, we have the involution acting by -1. So we can view V1 as R3 and B minus 1 as the complex plane quotiented with Z2, just because B minus 1 has an SU2 structure. And one can write the free-form phi as according to the pairing of the standard basis of R3 and the SU2 structure on this complex plane. So to resolve the local model, we can proceed as follows. Since now our local model is a product of two spaces, R3 is non-singular and the other is singular. So what we do is just resolving the singular parts. And this is like the topological resolution, but to resolve the free form, one has to find a SU2 structure on this resolution and construct the G2 structure in the same way as we did before. And well, it is well known that the resolution of our orbifold is the blow up at 0 of the complex plane quotiented by Z2. And one can view this blow up at the quotient of the standard blow up of the complex plane, which are the pairs of points on C2 and lines on CP1, such that the point lie on the line, and one has to quotient it under the action of -1 acting on C2. And the exceptional divisor of this resolution is CP1. And it's also like well known that this has an SU2 structure in which all the forms are closed, that is an hyperkähler structure. The forms omega2 and omega3 are the pullback of the ones in the base, and the symplectic form comes from the Eguchi-Hanson metric, but I'm not gonna go into the details of that. And finally, I will outline the construction of that proves theorem 1. We start by a left invariant closed to the structure on an nilpotent Lie algebra on the list, as I explained previously. This is the one we are choosing, and it is quite complicated, and it comes from like a parametric family of a 7-dimensional nilpotent Lie algebras. And the G2 structure is not written in the coordinates that yield the Salomon notation, which I am denoting by E1 to E7. But if one do a change of variable, defining some B1 to B7, one can write phi in the canonical form. And the important property is that B1, B2, B5, and B6 lie in the span of E1, E2, E5, and B6, and B3, 4, 7 lie in the span of E3, 4, 7. So the associated topologically, the associated Lie group is R7, and one can build a product using Baker-Campbell-Hausdorff formula. And then we choose a lattice on this space, and we define M as the quotient of the group by the lattice. And then one has to define an invariant Z2 action. So for that, the invariant Z2 action is the one that fixes E3, 4, and E7, and reverses the sign of E1, 2, 5, 6. You can check using this formula that it preserves the G2 structure. So what we have is a closed G2 orbifold. And an average argument yields that the cohomology groups of the orbifold are the the classes of the cohomology group of the manifold that are set to invariant. And doing a computation with this nilpotent Lie algebra, one can show that then the first Betti number of the orbifold is equal 1. And the action is also constructed to guarantee that the orbifold is not almost formal. In this case, in order to apply theorem 1a, one has to check that the isotropy, the fixed locus of the involution has an over-vanishing closed one form. But doing a computation, one sees that the isotropy locus consists of 16 submanifolds, and they are diffeomorphic to an Hill manifold whose Lie algebra is 0, 0, 1, 2. So every combination of the two first vector of the dual of the Lie algebra are gonna give by left translation the non-vanishing closed one form we want. So we perform the resolution using the theorem, and from the second theorem we obtain that the orbifold, the resolution is not almost formal because the orbifold wasn't, so it does not meet that torsion-free structure, and that the V1 is equal 1. I was listening something. Do you have some questions? Okay, if not, let me continue with the second exact data structures and compact quotients of Lie groups. It's a joint work with Fino and Raffero. The question was that let's consider G as a 7-dimensional Lie group admitting a compact quotient by a lattice. So the question is, does it admit a left invariant G2 structure? Before our theorem, Fernandez, Fino, and Raffero proved that the answer is negative if G is a semi-direct product of R with an important Lie algebra, and such that answer and Fiber and Salaman prove that the answer is negative in the general case that the Lie algebra was a semi-direct product of R with an nilpotent Lie algebra, eliminating the second condition that the other paper have. And as I said, we generalize this to all possible Lie groups G. And the strategy is to distinguish between solvable and non-solvable cases. And on this, we're gonna perform several tests to discard the existence of such a structure. In the non-solvable case, Fino and Raffero did a classification of non-solvable Lie groups admitting a closed D2 structure, well, a left invariant closed D2 structure. So we only have to focus ourselves in Lie groups appearing on their classification. And these are 4, and they have Levy decomposition, which is a semi-direct product of SL to C with centerless unimodular 4-dimensional solvable Lie group. And here I wrote them. So the first test is to check if these free forms, if these Lie algebras have exact free form that is also stable. Recall that for that, we consider the form, the bilinear form, using the wedge products of the contraction of alpha by U and the contraction of alpha by B, as I mentioned in the first slide. If this, like bilinear form is positive definite or negative definite, then the form alpha will be stable. But that's in the Lie algebras Q1 to Q3, we can check by maple that using maple that exact three forms are unstable. And the second if the associated connected group 1,4 doesn't pass the test. So now we have to we go to solvable Lie groups, and for that I'm gonna introduce the condition of being strongly unimodular, because that's a necessary condition for a solvable Lie group G to admit a lattice. So the Lie algebra, little d, and let n be the nil radical of the Lie algebra. And we denote by n0 to nk the descending central sequence. Recall that the adjoint map of every vector takes each of the elements of the sequence to itself. Therefore, it makes sense to consider maps, to consider the restriction of the adjoint to the quotient of ni over ni plus 1. So the condition of being strongly unimodular is that for every vector on the Lie algebra, this indacid map should be traceless. And a remark here is that strongly unimodular implies unimodular. So the setup for this will be the following. Consider a unimodular solvable Lie algebra endowed with a metric. Since the group is solvable, we can take S, a codimension 1 unimodular ideal, and we can take X, which will be a unit length vector that is orthogonal to S, to the ideal. Then one can write G as a semi-direct product of R with this solvable algebra by the map D, which is the adjoint map of X. And I'm going to employ the following notation. I'm going to call the differential of the Chevalley-Allenberg complex of G with G bar, and also going to denote by eta to the one form determined by the metric and the vector X. And I will call by D the differential on the Lie algebra S. And I'm gonna extend the action to the exterior algebra of S as a derivation, like this formula states. And well, non-difficult fact to check is that the one form eta is closed with the differential D bar. So now we're going to assume that we, in such a Lie algebra G, we have an exact G2 structure phi that indices the metric that we already fixed. Then, well, one can decompose phi according to the orthogonal splitting of G as R as the span of X and S, and write phi as a two-form omega with eta plus psi, where omega and psi are formed on S. And as so some slides ago, since the splitting is orthogonal, this omega and psi induce an SU3 structure on S. And if we have phi, if we have a primitive mu of phi, that is phi is equal to the mu, and we split again mu into the orthogonal splitting as beta with eta plus alpha, then like computing the equation phi equals d bar of mu, one obtains that psi, the free form of the SU3 structure, is the differential of alpha, and this condition only depends on the Chevalley-Eilenberg complex of S, and one also obtains that omega is the differential of beta plus the derivation d acting on alpha. And for explaining how we discard these like equations, I'm gonna do a short digression on SU3 structures and stable forms. An SU3 structure, well, is determined by a complex structure and a complex volume form, or equivalently a two form and a complex volume form. But in these cases, like the two form acting on UV equals the contraction of well, the contraction of the metric and the tensor G evaluated on UV. And this is a 1-1 form, and psi equals the real part of the complex volume form. And this form satisfies some conditions. First of all, psi is a negative stable form. And for defining that, one can consider the isomorphism of the space of five forms and the tensor product of the tangent space times the volume forms of M, whose inverse is just the contraction of a vector on the volume form. And one can define an endomorphism of the tangent bundle by this relation. That is, when we apply the isomorphism A to the phi form determined by the wedge of the contraction of psi by V and psi, this has to be the tensor product of K psi, or acting on V, tensor the cube of omega. And then we consider the trace of K psi squared up to a constant. And if this trace that I'm denoting by lambda is negative, then psi is negative stable, and one can write the complex form using K psi and lambda. And the other conditions are more or less obvious. The second is that omega is non-degenerate. The third one is that omega with psi equals 0 because omega is a 1-1 form and psi is a 3-0 form. And the fourth one is that the contraction of omega with J should be definite positive because this indeed coincides with G because of our definition. But the interesting thing is that a pair that satisfies these properties is indeed an SU3 structure with the metric provided by the formula we have already mentioned. And a remark is that the condition that lambda is negative doesn't depend on omega, because one can replace omega cube here with any volume form, and since we are considering the square of K psi, this doesn't matter. And to finish, I will outline like the strategy we follow for solvable Lie groups. Book has a classification of 6-dimensional unimodular solvable Lie algebras. So the only question we have to think about is that if on every S solvable Lie group on this classification, can we find a triple alpha, beta, D such that the semi-direct product of R with S is strongly unimodular, and the forms omega and psi defined by the equation we previously found is a SU structure. So for each non-nilpotent solvable algebra, because it was previously proved that we can exclude them, we check the following. First of all, is does the solvable Lie algebra admit an exact negative stable free form psi? So for this, we just take a generic exact free form, the alpha, and we compute its lambda invariant up to a positive constant, according to the remark I explained above. And if there isn't, we exclude this algebra, and otherwise we continue and we find a distinguished set of derivation such that the semi-direct product of R with the solvable Lie algebra is strongly unimodular. And for every two-form alpha, whose the differential of alpha is negative stable, and for every distinguished derivation, and for every one form, we define omega with the formula we have. And then we wonder ourselves if this omega can be non-degenerate, if it is true that omega with psi equals 0, and if it passes these two tests, then we compute J for the pair from the pair omega psi and check if the contraction of omega by J is positive definite. The issue is that there is no solvable Lie algebra that passes all these tests, so it's proof that there is no strongly unimodular Lie algebra admitting an exact J structure. And some comments is that well, for most of the computation we use the software Maple. And yeah, that's all I wanted to say. Thanks a lot for listening.
Thank you for a very nice talk. Are there questions?
Sí, Lucia.
Sí, yeah.
It could be that a solvable group which is not unimodular, okay, admits a closed G2 structure, and at the same time admits extra symmetries such that S is equal to G over H, where G is a unimodular Lie group.
Okay, can you repeat? I think I didn't got it.
No, because the theorem says that you cannot find this closed with. Can you show the theorem? With an exact,
Oh.
As a quotient, right?
Yeah, as a quotient. And
but I wonder what if I take S a solvable non-unimodular with a closed, but S is equal to G over H. It has a different presentation as a homogeneous space with G unimodular and with a lattice.
H is or
It's the isotropy. It's the isotropy. The S is equal to G over H.
Yeah.
H is the isotropy. I mean, it's a closed.
It's a connected Lie group, but might not be discrete, right?
No, non-discrete.
Okay, yes, yeah. Okay.
But G can admit a lattice, and then you may have a compact quotient. And I wonder if you look for examples in that kind of situation.
We didn't. I know that there is an example of Bryant that admits a closed G2 structure, but we didn't study exact examples there. We haven't done this.
But this is not the only one. There are other situations where there is a paper by the Bryant's student. What is his name? Ball, maybe.
Okay.
Where he finds another cases where this happens, and I think it would be interesting to know if there could be exact G2 structures there.
Yeah, the issue with this problem is that we relied a lot in the classification of Bock for dimensional unimodular solvable Lie algebra. This is like dimensionalist. So I don't know. We can given one check whether it admits an exact G2 structure, but we don't really have very general arguments that one can use in all the cases. So if there is not a list, then one at this moment we cannot prove a quite general theorem like that. But it would be interesting.
Of course. Yeah. But I was thinking in more in an exploration for examples.
Yeah.
Maybe there is one, so there is no proof.
Could be. I don't know.
Nice talk.
Thanks for the question.
Are there other questions?
Yes. Hi.
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 Hi. I was wondering, in the non-solvable case, how did you rule which technique, or what did you use to rule out the Q4 Lie algebra that it doesn't have? How do you show that it doesn't have any lattice? My question.
For this, I think that if the proof was somehow that if Q4 admitted a lattice, then the simply connected group associated to S, and then we prove, I think it was manually, that this simply connected Lie group doesn't admit a lattice, using that it should be bidirect product of R with another one, which let me check 1 second the conditions.
Okay, so you go to the solvable.
Yeah, it is. Yeah,
and for the solvable,
one,
you know how to show it. Okay.
Yeah.
Okay.
Yeah.
So.
Yeah.
Okay.
Yeah, it's a semi-direct product of R with R3, and with this you exclude that. Yeah.
And this is more or less general, that if you have a semi-direct product, then the solvable part has a lattice. If the big one has a lattice.
Yeah.
Okay.
The name of the paper, but I have a reference. Yeah.
Okay, I will take a look. I will take a look. Thanks.
Any other questions? If not, let's thank the speaker again. And our next talk will be in 2 weeks by Himanshi Shah. So thank you.